Now that we know how to do change of coordinates using our polar and spherical, we can do a change of coordinates dictated by the form the equation takes. So again, we'll start with a surface, and I can't solve for x, y, or z, so the default parameterization is no good. But I see a sum of squares group. X squared plus z squared, why not call that r squared? That gives me a triangle, just like in polar coordinates, except instead of using x and y, I'll use x and z. Where the x goes, where the z goes, horizontal or vertical, irrelevant. It'll change the geometry, but it's still a change of coordinates. Now I've lost a variable. Instead of 3 variables, it's 2 variables. R is always positive, so I can solve for it. Now that's an equation I can use to substitute. This first equation, can't solve for a variable, can't substitute. Do a change of variables, and I now am in a form that I can substitute. So the key is I've done a change of variables. I've done a change of coordinates. Every point in space, instead of being described by x, y, z, is going to be described by y, r, and theta. X and z have been replaced by r's and thetas. So my change of coordinates, y is still y, x is r cosine theta, and z is r sine theta. This is the change of coordinates. Now I can substitute the equation into the change of coordinates to reduce the number of variables. This is parameterizing. R gets replaced, so x is now a function of y and theta. R gets replaced, z is now a function of y and theta. 2 parameters. The way we're going to think about it is we're building up the surface one point at a time in terms of the parameters y and theta. Every point on the surface has an xyz coordinate, which I can write in terms of the parameters y and theta. 2 parameters, that's a surface. One equation, that's a surface. You want to always make sure that you got this basic number sense correct.